So we're going to have question period.
So,
okay, but he has a question that he has prior to the start of class. So what's your question? Oh, you wanted to see how it turned into box?
Yeah.
All right. So suppose our action density is d mu phi, or let me use Roman letters, dA phi, and with Schwarz's metric, this comes in with a plus sign, and then minus a half m squared phi squared. Okay? So then, what's partial L, partial phi, comma A say? Well, that is partial upper A of phi. Okay, or if you want, I should maybe write this again. D lower A phi is the D upper A. Now, you'd say, well, maybe there's a 1/2 here, but of course D lower A is just plus or minus D upper A, so you have to differentiate both, and you get a minus sign, but it's. Shall I? You don't want me to do this explicitly, right? We're happy with this, right? Is that right? Okay. So then you have D lower A of partial L, partial D lower A phi. Well, that's D lower A of D upper A phi. Okay? And what's that? Well, in Schwarz's metric, the time derivative doesn't have any minus sign. So this is just D double dot minus the square of the spatial derivatives. Okay? And then Lagrange's equation tell us that this is equal to partial L partial phi, which is minus a half, well, sorry, there is a factor of 2 there. So this is minus m squared phi. And so altogether then the equation of motion is phi double dot minus Laplacian phi equals minus m squared phi. And if you want, you can write that as box plus m squared phi equals 0. All right? Now, you had, I have to. Question. All right, your question.
So you always say like, well, this is the Lagrangian for this. This is the Lagrangian for EM. You know, and you work through it and go, look, it's good for, you know, if we learn a point source, it gives us the field. But how do you know these things? Do people just guess until they get it right? It just totally seems arbitrary. And how do you know those are unique?
Well, it may seem arbitrary here because what we're doing is talking about quantum field theory, and so we're talking about several different field theories, and so we say for this field theory we have this Lagrangian, for that field theory we have the other Lagrangian. If this were of course only in quantum molecular dynamics, then we'd write down one Lagrangian, one action density, let us say, and that would be it for the whole semester. So that's a partial answer. Another part of the answer is this is supposed to be the action density for a field that describes a particle of mass m. Well, we see here's the equation of motion, and we know that the solutions of this are plane waves, e to the I px or in other words, e to the I et minus p dot x. And moreover, this thing tells us that minus e squared plus p vector squared plus m squared is 0. That's what this equation of motion says. This is a solution, but a solution only if this is true. But this tells us then that E is the square root of, or plus or minus, the square root of p squared plus m squared. Well, this is the energy momentum relation for a particle of mass m. So that's that. The other case that we were talking about was where we would say that L is minus a quarter F mu, let us say FAB, FAB. Well, if you write FAB as DA AB minus DB AA, and then stick that in there, well, what you see is you've got that this is actually equal to E squared minus B squared. That's the action density of electromagnetic fields. And now, when we get to some other, now, first of all, are these actually true? And my suspicion is no. In other words, I think that we're dealing with quantum field theories here that are simple. These are the simplest choices that describe what we're trying to deal with. But as you know, there are infinities in quantum field theory, and I think the infinities come because our theories are too simple. Truth. And this is to some extent a minority viewpoint. Most people are very happy with the theories we have. Okay, any other questions? All right, now,
So the air?
what?
The air. You said you want to turn off the fan.
Well, you've got it running, right?
Turn off the air.
Oh, shit! You know, you've got to remind me with more vigor than that. And I meant you to remind me at the very beginning of the lecture.
I did.
You did?
Yeah.
Oh, and I just didn't hear you. All right, sorry. Okay, so what we're going to be talking about today, at least in the beginning, is what Schwartz calls old-fashioned perturbation theory. And we could just skip this chapter, but I think it's probably worth doing. We saw last time from the Lippmann-Schwingle approach that the T matrix, and remember what T does. T B is B. Well, actually, I don't even remember exactly what that equation was. So let me see if I can find it so I don't screw up which is the free state. Yes, okay. VC. So in other words, the eigenstate of the full Hamiltonian times the interaction is the eigenstate of the free Hamiltonian times T. And we saw that T then was 1 over 1 minus V 1 over E minus H0. And that was then a sum n equals 0 to infinity V 1 over E minus H0 to the n and times V. And so in particular, the the two lowest terms are the TFI, if we take an inner product of this with an initial state and a final state. This would be VFI plus the sum over intermediate states, VFN 1 over EI minus EN VNI. So I'm reviewing here non-relativistic quantum mechanics, and if we do scalar QED, I'm going to write it slightly differently from the way Schwartz writes it. I'm going to write it as psi dagger of x, phi of x, psi of x, where if we want, we can have an E for electron and maybe a gamma for phi for photon. So we're imagining that everything is a scalar field. And really, this is spin 1/2, this is spin 1/2. And okay, and for some reason, Schwartz left out the dagger and treated the electron as a neutral field. I don't know why he did that. So I'm doing it just slightly differently. And when you do that, you don't need the 1/2 here. So what are the two? Well, first of all, the very lowest. This thing here is not going to contribute, and we'll see why in a minute. Let's consider the. Well, maybe I should show that first. So what is the electron field? This is going to be an integral d cubed p, like any field, 2 pi cubed. And normalization, we have 2EP. And then we have something that annihilates the electron. And this is all at time 0. So we're doing this, we're doing stationary state perturbation theory. And so everything's at time 0. Okay, so this annihilates the electron. This creates positrons. And the opposite field, psi e dagger of x, of course, is just the same, except that this is dBp dagger e to the minus r px plus cp e to the I px. Then the photon field is an integral d cubed k, 2 pi cubed. Again, this is scalar 2 omega k. Something that annihilates the photon, e to the I k dot x, plus photon's neutral, so it's the same particle as the antiparticle. And all right, any questions? Okay, so let's let's just see that the initial, let's see that this term is 0. Well, what are the initial states? The initial state is E1, E2, so it's 2 electrons. The final state is E3, E4, that's 2 different electrons. And now, the only way to get from this to that is to have no photon operators and 2 electron annihilation operators, so that we rub out these 2 guys, and then 2 creation operators for electrons, so we create these 2. And we need to do that because these are different momenta. All right. Well, clearly we can't do that with this because we only have 1 electron annihilation operator here. We don't have any over here. And we only have here we have a photon annihilation operator, photon creation operator, so we wind up with a photon in the final state no matter what we did. So, the matrix element VFI, or well, VFI is this. So in other words, VFI, which is FVI, that one's 0. This is not a cause for celebration because, in fact, if this were non-zero, it would be much simpler than what we're about to count. All right, now what we're going to calculate then is the various possible intermediate states that can exist here. And Schwartz draws Feynman diagrams of these, and that's 1 comes in, or if you want, E1 comes in, 2 goes out. I'm sorry, 3 goes out. And 2 goes in, and 4 goes out. Okay. And now, we're emitting a photon that's later absorbed, and so this is called the retarded interaction. But the other possibility is that 1 comes along and becomes 3, and then 2 comes along and becomes 4, and emits a photon. And now the intermediate state is here and there. And so this intermediate state in this case, the state n then, what would it be? Well, it would be electron 3, the final state electron, some sort of a photon, and then E2. So it would look like that. And we're going to call that NR. And then the advanced one is this one. So that's 1. So that's E1, the photon, and then E4. So those are the 2 states, the intermediate states. Okie dokie. Now we're going to deal with these things. So there's going to be a 1 over in it. This is, of course, your energy denominator is what we call it. And then VNI and VFN. We're going to compute these 2. And what we're doing here is something in the context of non-relativistic quantum mechanics, really, in a sense. Well, sort of the field theory version, as close as field theory can get to non-relativistic quantum mechanics. But then on the other hand, what we're doing is very similar to what one does in full-blown quantum field theory. And so this is, so that's why it's useful to do this. So let's look at this n retarded, the E1, E2. So what is this? Well, it's going to be, as we saw, that was E3, E2, gamma, V, E1, E2, and now E2 is just a spectator here. And so that's just, we'll say it's normalized to unity. In fact, when you have these plane waves, they're normalized to 2 pi times the volume of the universe. And so that's not the same as 2 pi cubed times the volume of the universe. And so that's not the same as 1. But just between friends, let's just leave that E2. Well, if you want, you can just have it E2, E2. But the important thing then is E3 gamma V And so if we just look, and so this is just some overall factor that we're going to kind of ignore for the moment. It gets absorbed with various factors that we'll be talking about in chapter 5 when we get more serious about cross sections. And so this E3 gamma V E1, what is it? Well, there's an E, a d cubed x, field adjoint, electron adjoint, photon, electron. Okay. And so, oh, and let's make these states. Well, this E1, let me use this. E1 here is square root of 2 E1 times A1 dagger, no, not A1, B1 dagger on the vacuum. I'm referring to the equations in chapter 2 where he says that the normalization is you have ground state, creation operator, square root of 2E1, that's the state. And so that's the E1, that's what E1 is, but this, and the state E1, E2, then would be that, so in other words, E1, E2 would be square root of 2E1, 2E2, B1 dagger, B2 dagger, vacuum, or ground state. But we're ignoring E2, and so what we've got here as this, we have here E1 dagger, and then a square root of 2E1. So that's the initial state. The final state, well, is an E, which is the coupling constant. And now this state, which is E3 gamma, well, this would be square root of 2E3, square root of 2 omega k, whatever, or omega gamma, whatever it's saying. And it would be B3 dagger, A gamma dagger on the vacuum. But the adjoint of that then is E3 gamma is the square root of these energies times 0 B3 A gamma. So this is B3 A gamma square root of 2E3 2E gamma. Okay, now what's the rest of this? So those are the final state and the initial state, and then we've got an integral over space, and then 3 fields. So that's integral d cubed x. But now each of these fields is an integral dp or d. I'm going to use p for the for this integral. I'm going to use k for that one and q for this one. And so this is integral d cubed p, and each of these. Well, if I absorb all of the 2 pi's, you have 3 factors of 2 pi cubed, so that's 2 pi to the 9th. And then you have, in the definition of the fields, you have a 1 over square root of 2EP. So you have a square root of the product of all of these energies. So what do we have here? EP 2 omega k, and then 2EQ. Okay. And then you've got d cubed p, d cubed k, d cubed q, because of all these things. And then what do we have? We've got something to create this electron in the third state here. And in fact, since we've got a B operator, we're going to have a B dagger sub P, and this will be, when you create this, this will be e to the minus I P dot X. And these are all three vectors. And then you've got something to create a photon. And so we have AK dagger, and that comes in with an e to the minus I K dot X. And then you've got something that annihilates this incoming electron. And so that is an A, no, not an A, it's a B. B, and what did we say we were going to use for that? Q. E to the IQX. Okay. And I've left out all of these extra terms that aren't helpful for the thing that we are computing. They contribute to other processes, perhaps. And remember the normalization that Schwartz uses is 2 pi cubed delta cubed T minus. All right, well, what happens here? Well, this B on that is gives us a factor due to the commutator. In other words, another way of writing it is BQ times B1 dagger is equal to BQ B1 dagger commutator plus, of course, B1 dagger BQ. But B1 dagger BQ acting on the vacuum, 0. Big times 0. Okay, so when I was in elementary school, I was a class clown. I guess that wouldn't shock you. Okay, this commutator is 2 pi cubed times the delta function. And we're going to have 3 of these commutators, so that cancels the 2 pi to 9. Yes?
Did we just switch from indices being momenta to indices being integers?
I'm sorry, say that again?
So the Q is a vector.
Yes.
And then what is the 1?
Oh, 1 refers, good question. Do you want a candy?
Hell, thank you.
The 1 refers to the momentum of the incoming electron.
But we will fearlessly just take.
Huh?
We will just fearlessly.
Well, just imagine that's
2 minus
P1.
1 is okay.
But you're absolutely right. This would be delta 1 minus Q, which is kind of dumb.
No, unusual is how I would phrase it.
This is a hybrid notation.
There we go. Not for the finger part.
All right. Let me get another chalk here. I'm out of tea. I did bring a joke, however. All right, so that's that one. We see how it occurs, and it's always this way, by the way. Throughout quantum field theory, it's always like this, with the exception of the case where you have fermions. When you have a fermion, what you do is you say this thing is the anti-commutator minus the thing in the other direction, and that one's still 0 on the vacuum. And then the anti-commutator is something like this. Okay, so what we've got then, when we finish, is what? The 2 pi's are gone. we've got all these, the three momenta all have to match. And so these delta functions, this delta function, for example, says that the integral dq is just going to replace q everywhere with, say, the momentum of the initial electron. And so this E becomes the energy of the initial, well, this E becomes the energy of the initial electron. And then that 1 over 2E1 cancels the square root of 2E1 here. So all the E factors cancel. What is left? What's left are the phase factors. So this, and the E out in front. So there's E integral d cubed x, e to the I, and the phase factors are P1 minus K gamma minus P3 dot x. So in other words, maybe we should just do one more. This creation operator, we have vacuum B3, this creation operator. Well, how does that work? Well, it's vacuum B3, and it was BP dagger. Well, this thing is equal to 0 BP dagger B3 plus B3 BP dagger commutator. That on that is 0 because it's the adjoint of BP on 0. So this is 0, and then this thing is 2 pi cubed delta cubed of P3 minus PP. That's what sometimes people call Netanyahu. His first name is Bibi, and he said once to some reporters were calling him Bibi, he said, you know, I'm president of Israel, you should use a little more respect and call me by my full first name or something, or by my last name, and so the reporters started to call him Bibi Netanyahu. Anyway, so this thing is P3, delta of that minus P. It isn't PP, it's just P. Whatever, that is an integration variable. Okay, and then this thing turns the P variable into P3, and we get a 2 pi cubed. Okay, so when we're done, we've got that. And of course, that is simply E 2 pi cubed delta cubed of P1 minus K gamma minus P3. And so what's happening is that momentum is conserved at this vertex. All right. Now we have to do this vertex. So this would be VFN. And okay, so what is VFN? Well, it turns out that it's almost the same. That would, so VFN turns out to be E3, E4, V, and R. And so that's E, E3, E4, V, E3, E2 gamma. And so that gives us E, and then there's this E3, E3, which is just a number by volume universe. But anyway, and then what we have is E4V, E2 gamma. And if you compute this using the same recipe, what you get is simply ignoring the E3, E3, you get E 2 pi cubed delta cubed, and it is P2 plus P gamma minus P4. Well, I called it K gamma there, so maybe, I don't know what to call it. Well, if we call it K gamma or P gamma, depending on whatever you prefer. So that's so now we've done the retarded case, and of course we need to compute this. And what are these energies? Well, the intermediate state has the energy of the final electron, E3, plus the energy of the photon there. And the energy of the photon is the length of P gamma. And the energy of the second electron. All right. Now, the next we have to compute the advanced case. So that's E3, E4. By the way, all of all of these particles in these states, of course, are physical particles. That's the way we're thinking of this. And consequently, the photon is moving at the speed of light and has the energy is equal to the length of its momentum. And so it's said to be on shell. That's what on shell means. On shell means that that E squared is equal to P squared plus M squared. E squared is equal to momentum squared plus mass squared. That's on shell. It's just jargon. So this one is E3, E4, the E1, E4 gamma, and if we drop the E4, E4 term, then this is equal to E3V E1 gamma, and then this is altogether E 2 pi cubed delta cubed P1 plus K gamma minus P3. Oh hell, wait a minute. Yeah, right, that one's right. Okay, but I did the second. I need to do one more that I got out of order here. I should have done NAV E1, E2, and this is E1, E4, the gamma, V, E1, E2, and so this, again, ignoring the E1, E1, this is E4 gamma, V, E2, and so this is E 2 pi cubed delta cubed of P2 minus K gamma minus P4. Okay, so those are the two terms, and let us compute what this En is. En retarded is E3 plus E2 plus omega k, and because of that delta function, omega k is just P1 minus P3. So this is also the same thing as E3 plus E2 plus P1 minus P3. And now En advanced is E1 plus E4 plus omega k. And in this case here, this is P4 minus P2. Wait a second, this is the minus one. So it's P2 minus P4, which makes more sense. here is we have to integrate over these intermediate photon momenta, d cubed k gamma and 2 pi cubed omega p, and we have e squared 2 pi to the 6th there, and then delta q p1 minus k gamma minus p3 delta q p2 plus it's minus p gamma. I think that's right. Okay. Divided by E1 plus E2 minus, so this is EI, and E intermediate is E2 plus E3 plus P1 minus P3. And then the other term is also a d cubed k gamma e squared 2 pi to the 6th. Again, these delta functions p2 minus k gamma minus p4 delta cubed p1 plus k gamma minus p3, and we have E1 plus E2 minus E1 plus E4 plus omega gamma. Well, I'm writing omega gamma. This is also omega gamma there. And in a sense, this I should have written omega gamma, I guess, since I'm still integrating here. And what we wind up with then is e squared 2 pi cubed over 2 p1 minus p3 and 1 over E1 minus P3 minus P1 minus P3. Well, I don't know where this is. Plus 1 over E2 minus E4 minus P2 minus P4. And there's an overall delta function. In other words, when you integrate over k, this is a k gamma. Well, I have k. When you integrate over k, one delta function cancels this and says you have to replace k by p1 minus p3, say. Then you have that other delta function you stick here in. In other words, this second delta function becomes delta cubed p2 minus p1 minus p3 minus p4. Well, this is, maybe this should have been a plus. Then this, if this is a plus, then this is p1 plus p2 minus p3 minus p4. That's energy momentum conservation. In 3 dimensions. And so this is P1 plus P2 minus P3 minus P4. All right. Now, if we say, just as notation, if we say E1 minus E3 is delta E, then we also have, and this, you know, when you do stationary state perturbation theory in quantum mechanics, you also have conservation of energy. And so if we impose conservation of energy, this gives us that this is equal to E4 minus E2. And so I'm adding this, just referring to your experience with stationary state perturbation theory in quantum mechanics. So all together then, what we've got is TFI is E squared 2 pi cubed and 2 omega k 1 over delta E minus length of k being the photon, plus 1 over minus delta E minus length of k. By the way, don't sweat the overall factors too much. I mean, I just realized that I left out the, I may have left out a norm of E1, E1, or E2, E2, and so forth. See, it's the essence of this is what I want you to learn about, and we'll do things more carefully later. All right, so what happens here? You add those two things together, and what do you get? Well, you get E squared 2 pi cubed 2 omega k, and adding these together, what we get is delta E plus length of k over delta E squared minus k squared. And then over here you have minus delta E plus length of k. So when you add these two things together, in other words, effectively you have minus and then plus plus. So let me make it that way, make it a little bit simpler. Now you multiply the first ratio, top and bottom, by delta E plus k. And the second one you multiply by delta E minus k. And then you have the minus sign, and that becomes. So the delta E's cancel, and what we wind up with is E squared 2 pi cubed 2 omega k. And then we have a 2 omega k up there, delta Q P1 plus P2 minus P3 minus P4. And then the crucial thing is that it's delta E squared minus k vector squared. Or if we cancel the 2 omegas, we get E squared 2 pi cubed delta cubed of energy momentum conservation. And we're dividing simply by k squared, where k is delta E k vector. Now this is not an on-shell photon. Okay? Because delta E, you see, in other words, this is, what did I say that was? E1 minus E3. This is E1 minus E3, and this is the momentum of the exchanged photon. And the length of k is not necessarily equal to E1 minus E3. And so consequently, this is an off-shell photon. So the point here is that we've gotten to a result that we'll see later when we do things in terms of Feynman diagrams. This is just the photon propagator here. And in other words, 1 over k squared is minus 1 over box. And what we would say in a Feynman diagram is we have one electron going along, exchanges a photon, and this thing here is a Fourier transform of 1 over k squared, where, when I say Fourier transform, I mean d4 k over 2 pi to the 4 k squared plus or minus I epsilon, I forget which, e to the I k x minus y. And if, in other words, if that's x and that's y, then this is the photon propagator. So what we've seen here is that it comes about in terms of ordinary quantum mechanics in a calculation in which all the states are physical or on shell, and in which the vertices vanish unless momentum is conserved. 3 momentum, not 4 momentum. And the energy is not conserved at each vertex. And of course that's necessarily true because what you've got is E initial minus the intermediate energy. If the energy were conserved at the first vertex, then you'd have that E3 plus E gamma plus E2, or rather, what would it be? It would be E1 plus E2 minus E3 plus E gamma plus E2. If the energy conserved here, that would be 0. And then you'd get 1 over 0. And we have lots of infinities in quantum field theory, but not that many. Okay. So there may be some questions at this point.
Yes.
Yes.
So what's the length of that k?
What is the what? Length
The length of that k.
Of that k?
Right.
Well, let me go back there and what we said here was that this 3k is P1 minus P3. So it's whatever P1 minus P3 is. Because momentum is conserved at the first vertex.
So it's arbitrary.
Hmm?
It's arbitrary because we don't know the final state if we.
Well, no. We assume that we're computing the amplitude, or we're computing the T matrix for a given initial state and a given final state. So we know P1, P2, P3, and P4. And now what we're saying is that when you do that calculation, what you find is that the non-trivial part is 1 over k squared, where k is a 4-vector E1 minus E3, and then k, and k is in fact P. In fact, what is this? This is the, if we think of these as 4 vectors, this is P1 minus P3 as 4 vectors. You see, because that 4 vector here is E1, P1 minus E3, P3. So the first component gives you that, and the difference in the 3 momenta give you the 3 momentum of the photon. But now this then is 2 4 vectors that are electron 4 vectors, and the difference of 2 electron 4 vectors is normally not a photon 4 vector. In fact, it's probably some algebra would be doing the right algebra. I think you can show that never happens. But here's P1 coming in, there's P3 going out, and so you see the 4 momentum on this line, if we conserve 4 momentum at each vertex, the 4 momentum on this line is P1 minus P3. And that's the K that we wound up with in this roundabout way where I set 2 and 2 pi and 1 and 2 pi cubed times the volume of the universe all equal to 1. Also, there may be an overall factor of 2 that I'm passing up, okay? Because we said here, all right, I'm
So what
I'll
if
leave that aside. There may be an overall factor of 2 that is screwed up. Because, all right, let's forget about that possibility. Any other questions?
what if we don't know the final state? Because in classical mechanics we just know the initial state and we know the final state.
Great question, great question.
I don't need
I
another
know,
one.
you're starting a candy store, I gotta help you out. Okay, that was a very good question. What if you don't know the final state? Because in fact, the whole point of classical mechanics is to predict the final state. What we learned in going from classical mechanics to quantum mechanics is we can't predict the final state, we only predict the probability of the final state. So, yes. And so here we're predicting the probability that if you have electron E1 and electron E3 coming together, what's the probability, I'm sorry, E1 and P1 and P2 coming together, what's the probability to get P3 and P4 in the final state? So that's what we're computing here, that probability. And of course it's related to the absolute value square of the T matrix element, which is what we compute as an amplitude, is the absolute value square. Modulo factors of overall factors. Is there another question? All right. Okay. The last part of chapter 4 is Schwarz's way of introducing us to some of the infinities of quantum field theory. And the first one that he mentions, of course, is the worst one of all, namely that if we take this theory, say, and we compute the Hamiltonian and use for phi this expression, well, what we find out after a while, and making a calculation that takes a few minutes or a few hours, depending upon whether you've seen it before, you wind up with AK back at AK plus a half times omega k and a d cubed k. And this, of course, is a quartically divergent integral. And this is actually the energy density. Anyway, this you can see that this integral is quartically divergent, even if you take the mean value in the vacuum, because then what you have is a half integral d cubed k 2 pi cubed. This is just length of k. And so, I mean, this is just, you know, this is just completely nuts. It's 1 over 2 pi cubed, and then it's a 4 pi from the angular integration. And then you have a k squared. So you have k cubed dk 0 to infinity, which of course is, apart from the prefactor, it's infinity to the 4th power. Well, divided by 4. And so that's one of the problems that's still plaguing quantum field theory. And of course, what people said originally, way back in the, I guess, 20s or early 30s when this was noticed, was, well, this is just the energy of the vacuum. We can only measure the energy difference between two states, and so we're only going to. So this will cancel, and it's unobservable. It's meaningless. Of course, on the other hand, if you bring in general relativity, then this says you have an energy density everywhere, and it's positive, and it's infinite, and so that would cause the universe space to expand infinitely fast, exponentially, infinitely. I can't even put the adverbs together, but it's an exponentially quick, infinitely, to expand exponentially and infinitely fast. Whatever. Anyway, you get the idea. It's very bad news, contrary to experiment. What is true, though, is that maybe 10 years ago or so, maybe 15, maybe 20 by now, people realized that maybe that a few billion years ago the universe, the expansion of the universe started to accelerate. And so, in other words, if we could calculate this correctly, we might find in the right theory that the energy density is some finite amount. And it's, I don't know, it's of the order of millielectron volts to the fourth power is the actual energy density. Anyway, so what, let me try to finish chapter 4 now. The first topic is just to do the Stark effect again, but thinking of it first in terms of an external field. And by external field, you mean that the field is classical and it's something that you can control and set to any arbitrary value. And so what the Stark effect is, of course, is you put an atom in an electric field, and then you measure the changes in the energy levels. And the interaction, let me write it as H sub I guess. It's E dot X, or if you want E absolute value of E times the direction, the X in the direction of E. And now it turns out that, that the lowest order matrix element of this, say E0 or ENHI, sorry. That's 0 because states don't have electric dipole moments. Because, in other words, this would be EE times, well, let me just call it N, X, N, and that's 0. Okay. So you go to second order perturbation theory, and now you have delta E0 is then a sum, and I'm considering the shift in the ground state for simplicity. So you sum over excited states, and it's easier, let me say that, 0, this means the ground state of the atom, okay. HI, N, HI, 0 over E0 minus En. On the other hand, the unit operator is the ground state plus a sum over the excited states, n greater than 0. And so consequently, 1 over En minus E0 is less than 1 over, well, E1 minus E0, because E1 is only a little bit bigger than E0, let us say. And so, if we put a minus sign here, then we get minus delta E0 is the sum n greater than 0, 0, HI, NN, HI 0, and we divide by En minus E0. On the other hand, that's less than the E1 minus E0, so we can pull out the 1 over E1 minus E0. And then what we're doing is we're just summing over n greater than 0, 0, HI, N, HI 0. And now this thing is just 1 minus 0, 0. And so that's equal to 1 over EI, E1 minus E0 times 0 HI 1 minus 0, 0 0. No, HI. HI 0. So I've replaced this sum over the intermediate states greater than 0 is 1 minus the outer product of 0 of the ground state with itself. And so now when you work that out, this is equal to ground state HI ground state. So that's HI squared 0 minus ground state HI 0 squared, all that divided by 1 minus E0R. So in other words, this change is negative, minus it is less than these finite values, and these things are finite because that's finite, and this is just mean value of x squared in the ground state, and this is, well, this thing should be 0 actually, because the ground state of, because there are no dipole moments. So that's that. Then Oppenheimer said, well, suppose we do this in quantum field theory, and instead of having the photons due to some classical electric field, let's have the photons be the photons that come from the fundamental interaction, which I thought I had written, did I never write it down? Well, the fundamental interaction, of course, is, I hope I wrote this. Did I ever write this down? E, at a given point, it's E psi dagger phi psi. I wrote it down as good. Thank you. And if you want, you integrate that over all space, actually. So this is X, electron, gamma. All right. So Oppenheimer said, well, let's compute this where the photon is not an external photon, but actually comes from this fundamental QED interaction. And so what he was doing then was saying that H0 was H0 atomic plus H0 photon, and of course H0 photon is this. Okay. And the general state of H0 then is some state for the atom, and then n photons of momentum k, and this gives you En plus the sum nk omega k on psi n nk. All right, so that's the general state of the theory. Now, if you actually do this, what you get is this divergent integral, although it's not nearly as bad as the energy density of the vacuum. So, I mean, that shows you that there's something nuts going on. I mean, you compute a real process, you get a divergence, that's bad. But what's even worse is you try to compute the energy density of nothing, and you get a worse divergence. So there's clearly something absolutely sickening about this theory, but anyway. Delta E0, what would it be? It would be like this. Delta Q P, delta Q K. K is the photon momentum. And we're going to have, let us say, pi to the 6th. And we're going to have an integral over space, because that's what we've got with this thing here. And now, what's happening? Well, if the problem occurs when the photon energy is high. Well, if the photon energy is high and the poor atom is just sitting here, it gets whacked by that photon, so the intermediate state of the atom is basically, has a momentum the same as that of the photon, essentially. And so what you've got then is e to the I k minus p dot x over E0 minus p plus k. And what is this? Well, this is a divergent integral. The d cubed k gives you a delta function, and so we wind up with d cubed k over 2 pi cubed, 1 over, let us say, minus 2k, and so that turns out to be minus infinity. That's because this is k squared dk, so this is an integral dk k, and so that's infinity squared over 2 times whatever the prefactor is. And so that's characteristic of all these problems that one has in quantum field theory. I thought I would, I promised you a joke, and the joke is actually a true story. As you know, Oppenheimer was somewhat persecuted in the 50s, early 50s or late 40s. And the reason was that Louis Strauss, who was a commissioner of the Atomic Energy Commission, was a very powerful man, was also very sensitive, and on the other hand, Oppenheimer was somebody who was not only gifted in mathematical physics, but he was very gifted verbally. He came from a very educated family, and he, unfortunately, he liked to make fun of people, especially people he thought should be made fun of. And Louis Strauss was one of them. Louis Strauss, it turns out, was concerned that the U.S. would export radioisotopes and that these could be diverted to military use. And the AEC ruled against him 4-1, but Strauss was a very powerful man, so he tried to get it reversed. And so Oppenheimer was called to testify in the Senate office building, and he said, "No one can force me to say that you cannot use these isotopes for atomic energy. You can use a shovel for atomic energy. In fact, you do. You can use a bottle of beer for atomic energy. In fact, you do." Now, that was bad enough, but then he went on. He said, "My own rating of the importance of isotopes in this broad sense is that they are far less important than electronic devices, but far more important than, let us say, vitamins, somewhere in between." And when Oppenheimer was leaving the caucus room of the Senate, he asked his lawyer, "Joe, how did I do?" And the lawyer replied, "Too well, Robert, much too well." And that was the origin of Strauss's anger, and since he was so powerful, he carried it out, and he managed to get Oppenheimer's security clearance revoked, and that gave people the impression that he was somehow a traitor or something. So it was another story is that Fermi, when Fermi heard that Strauss had revoked Oppenheimer's security clearance, Fermi said, "Oh God, now we'll all have to defend the son of a bitch." Fermi didn't like Oppenheimer because Oppenheimer was always making fun of people. I don't think he could make fun of Fermi, though. Or, I mean, he probably could try, but Fermi was head and shoulders above almost anybody at that time. All right, well, we've got 4 minutes, so maybe I will say what one actually does. Well, one does in quantum field theory to cancel these infinities, of course, is one says, well, in this action density, we don't really know what this m is. This is just a parameter. Let's say that it's the physical mass squared plus some infinite term, and we'll use that infinite term to cancel some of these infinities. And this field, well, what do we know about this field? Is this the field that has the ordinary canonical commutation relations, or should we scale them by some factor that would be infinity plus 1, and we'll use the infinity to cancel some of these other infinities. And then we have a charge. We don't have not a charge, we don't have an interaction. So we'll set the charge equal to infinity plus the actual physical charge. We use that infinity to cancel things. So we have 3 infinities. And it turns out, in sufficiently simple theories, that you can carry this out. These theories are said to be renormalizable. And I shouldn't make fun of them because, in fact, in quantum electrodynamics, you can calculate the magnetic moment of the electron or other things to several decimal places, and you get the right answer. So, and the standard model, of course, is such a success that it's a bit of a disappointment because even at the LHC, we don't see any hint of new physics, and so that's sort of that. So we do have a tiny bit of time left, so 2 minutes, say. So let me say something in a couple of minutes. What we're going to be talking about is what's called the S matrix. So this will give us the amplitude for some process in which an initial state goes to a final state. So the idea is you have an initial state, well, I mean, in general would have n particles, but I mean, give me a break. Let's have 2 particles, okay? And either one particle is aimed at some particle at rest, or you have a colliding beam accelerating you have 2 particles aiming at each other. Then the final state, F, could be several different particles. Right? And we're going to be using the Heisenberg picture to think about that. So all of the time dependence goes in the operators. The initial final state are at, in a sense, time 0. And in the Schrödinger picture, this is in infinite time, initial state minus infinity. And if we look at the Schrödinger picture, then what we imagine is that these particles are traveling without any interaction, and then when they get close enough, we imagine that we have interactions, and then they again get very far apart, and we imagine that they don't interact. So the point is, we will be talking about asymptotic states, and then when we discuss the asymptotic state, we'll be using the free field theory, and then we'll be using the full theory, you know, from for the relevant period where they're within a meter or 10 meters of each other, and then we'll use an asymptotic theory for the rest of it. And that we do that because it simplifies the way of thinking about things. All right, so that's all. We've run out of time. So you're going to turn it off, right?